So in this video, we'll do an example of a delta G calculation. And what I mean by delta G is that we're not under standard conditions. So let's start with a reaction. So let's say we want to get rich quick. So we're going to make some diamond. And we're going to make some diamond from, carbon dioxide in the air. Why not, right? So this would be an excellent way for us to get rich. So we're going to take some carbon dioxide and we're going to convert it into diamond. And we're going to make oxygen. So this sounds fantastic, right? So we should definitely do this. We can calculate delta G standard for the reaction. And maybe you can pause the video and take the Gibbs energy formations to the right and use them to calculate the standard Gibbs energy change for this reaction. All right, pause and go. All right, so if you're back, so we're going to go ahead and we're going to take the Gibbs energy of the products and subtract from the reactants. So we got diamond, it is 2.9. And we've got some oxygen, it is 0. And on the left-hand side, we've got some carbon dioxide, so it is minus 394.4. And those are all units of kilojoules per mole. So if we go ahead and we do that, we can see, this isn't looking good. That double negative is a positive. So essentially, we're going to be adding these two numbers together. And when we do that, we get positive 397.3 kilojoules per mole. Alright, so that is not very favorable, but hold on 1 minute. That just means that when we are under standard conditions, so our carbon dioxide that we make is 1 atm, and our carbon dioxide we use up is 1 atm, and our oxygen we make is 1 atm, it's not going to go. So maybe we can tweak the chemistry here a little bit. So we know the equation, delta G, is delta G standard plus RT natural log Q. So we'd really like to get this term here extremely negative. So we know it depends on the reaction quotient. So let's write the reaction quotient out. So the reaction quotient is the pressure of oxygen divided by the pressure of carbon dioxide. So notice that solids have an effective concentration or pressure of 1. O2, there's just one of them, so we don't square it or cube it or anything like that. Same with CO2. So that's products over reactants. We can also see that to get Q as small as possible, we probably need to get the pressure of oxygen really low and maybe the pressure of carbon dioxide really high. So we can go ahead now, we can build a business plan. So perhaps we are offering to run this as follows. So we're going to say, well, we're going to run and produce oxygen at very, very low pressures. And we're going to start with carbon dioxide at very high pressures. And maybe now this process will be thermodynamically favorable. So we're going to start with carbon dioxide at 10 atmospheres. And we are going to convert it into pure diamond. I'll just write it like that. And very dilute oxygen gas. So oxygen gas at a pressure of 0.00010 atm. So maybe you can go ahead, and we're going to do this at 25 degrees C just to make life easy. And actually, technically, these here only correspond to 25 degrees C. So go ahead and calculate. Can you get rich from this scheme? Is it possible? Is delta G favorable? So pause the video and have a go. All right, so if you're back, we can go ahead and we can try and do this now. So delta G is delta G standard, so positive 397.3 kilojoules per mole. All right, and then we're going to add our correction terms. So that is plus RT log Q. So R is 8.3145. Now it is joules per mole Kelvin. So we got to be a little bit careful there. We want to get maybe both these things in kilojoules. So we know that 1,000 joules is a kilojoule. So now that means we'll have kilojoules in the first term and kilojoules in the second term. T is 298 Kelvin. And then we've got the log of Q. Q is the partial pressure of oxygen over CO2. So that is 0.00010, all divided by 10.0. And if we go ahead and we calculate that, and I'll just move the screen up just a smidge here. So when we go ahead and we calculate that, we get delta G is positive 397.3 kilojoules per mole. And then the second term corresponds to a reduction of 28.5 kilojoules per mole. And we can see that actually it's not going to end up being negative overall, right? It'll end up being positive 368.8 kilojoules per mole. So unfortunately, it's not going to be spontaneous, but maybe we can play with this a little bit, right? Now we know how to calculate what will happen. Maybe we can start with CO2 instead of 10 atmospheres, 100 atmospheres, or 1,000 atmospheres. Now, the question is, how do we pressurize it? We probably have to pay a lot of money to get it under that pressure, and it might blow up. But we can probably thermodynamically calculate at what point can the reaction actually occur. Unfortunately, this brings us on to a fact that just because it can happen doesn't mean it'll happen quickly. So we haven't considered the kinetics of the problem. So thermodynamics tells us, are things possible? Kinetics will tell us how fast. So we probably shouldn't get too excited. Although, if you write a business plan and this ends up making you a multi-trillionaire, I would appreciate maybe, I'll take 10% or no, 1% of the profits would be fine. All right, thank you.